Hello, it's James from XRobots.co.uk. This is part 3 of my Star Wars Episode 7 BB-8 droid, which is a new droid that rolls along on a ball. As I said last time, I actually started this project before the real BB-8 was brought out on stage at Star Wars Celebration at Anaheim, so I didn't know what it looked like, but I've decided to complete this project anyway. So I've already done 2 parts, and the principle for this project is that I've got this robot with omnidirectional wheels and some accelerometers and gyros in, which actively balances on the ball, so it's like a 2-axis Segway scooter. And I actually got that up and running last time when we looked at the code. All of the CAD and the code for this is totally open and free, so have a look at the last part and have a look at the link in the description to this video to my website where you can find out more about it. You can see pictures of the construction and links to where you can download all the stuff. Since the last part was published, a couple of people have pointed out a couple of errors in my code, or at least one really big one. So I've actually done a little tweak to the code. We'll have a 30-second look at it. The droid is much more stable now. And in this episode, we're hopefully going to make it radio controlled and make it go a little bit faster. So this will probably only mean anything to you if you looked at the code review that I did last time at the end of the last episode. Basically, I'm using 2 PID loops to drive the axis, which are these statements here. And they have various settings for proportional, integral and derivative amplifiers within that PID loop. Basically, it tries to fix the gain and also looks at errors over time. So my loop is running at 10 milliseconds, so every 10 milliseconds, which is 100 times a second, it checks the sensors and tries to correct its balance. I actually found out, and thanks to the couple of people that told me, the PID loop itself has its own set sample time parameter. The default is 200 milliseconds, which is only 5 times a second, and I didn't set that, so it was left at 200 milliseconds. So I've now gone back into the code and I've set that to 10 milliseconds for each axis. And now I found it's actually much more stable. So previously my integral setting, which is the middle parameter there of the PID loop, was set to 0. And I found if I set that to any number it made the droid really unstable. I've now set that to quite a high value of 7. I've also trimmed down the dead spot, which is where the motors don't run at all, to 2 degrees from 3 degrees. And I've tweaked the other variables on that PID loop. And it's been much easier to tune up and the droid is much more stable. So let's have a look at how it works. So in appearance it's not too much different to last time, but it is actually much more stable and it's able to compensate for short, sharp shocks. So if I get something like this and go and hit it, then we can see that it does that little oscillation and then it goes and compensates again. Similarly, I can push it along if I'm gentle with it, and basically everything's good. So we could go and bias the motor slightly and make it radio controlled just by spinning them very slowly, but this is about the maximum speed it can do. If we push it too hard, then the motors go the fastest they can and off it goes. So what do we need to do to make the motors go faster? Well, the motors are currently running on 11.1 volt LiPos, but they're actually 24 volt motors, so we could run them twice as fast with a lot more torque. So that's going to be the intention for this episode. The other parts we've got in here are an Arduino Uno, which is controlling everything. I'd intended to use the Arduino Pro Mini from SparkFun Electronics, which is much smaller. But for now I've got this nice big programming socket on the Uno and I'm reprogramming quite a lot through trial and error to make this work. So for now I'm going to leave the Uno in there, but I'm pretty sure this is going to come back pretty soon. The other things we've got in there are the SparkFun Electronics 9 degree of freedom accelerometer, gyro and magnetometer, which is on a breakout board, and there's an Arduino library, so have a look at the last part, as well as the link in the description to this video to my website where you can find out what the parts are. We've also got a level shifter there to run that on 3.3 volt I2C bus because the Arduino is a 5 volt version. The motor controller itself is hidden underneath that breadboard. Don't know if you can just see the red board in the bottom there. And that is the SparkFun Rover 5 board, which is conveniently a 4-motor controller board. And it works in quite a good way where it only needs 4 PWM pins, one for each axis for speed, and 4 digital pins for direction. So that means we can run those 4 motors with PWM independently from the Uno or the Pro Mini, using only 4 PWM pins and 4 digital pins. Now these Arduinos generally only have 6 PWM pins on. We'd have to upgrade to something like a Mega if we needed any more. However, the Rover 5 board, as well as supporting wheel encoders, which would be quite useful for this sort of project if I were using them, and current sensing, only goes up to 12 volts. So I'm going to experiment with trying to run the motors faster, but to do that I'm going to switch out the motor controller for an L298, which is a standard dual H-bridge part. Now you can buy these at Spark Fun Electronics. I actually have one of these in my spares box already. The L298 is quite a standard part that's been around for years, but it does need 2 PWM channels for each motor. So in this case it's not too bad because I can run the motors together. It just means I can't run the motors independently, and the plan was to be able to spin the head by running them all in the same direction. I could do that with the Rover 5 board because they're all independent. With this I won't be able to unless I have 2 of these to control the 4 motors and upgrade to an Arduino Mega with more PWM pins on. So for now I'm just going to use one of these and lock the axis together for X and Y so they both turn in the same direction, and we'll see how much better that makes the droid. And hopefully I can make bigger sweeping motions as well as drive along at a reasonable speed. Right, everything's been completely rewired for 24 volts. So this is the Rover 5 board, which is quite a good board. I'll keep this for another project. I really like the wheel encoder inputs that it's got and the other features. But there we go. So the L298 is now on the robot here. And the wheels do go a lot quicker on 24 volts. So hopefully they should have more torque at low speed as well. So I'm pretty sure the higher torque is helping it stay more stable there. I've still tuned the PID loop up quite tight, so there's a tiny amount of oscillation, but on the whole it's pretty stable, and it can survive short sharp shocks and also these much bigger motions. So if I really give this a bit of a shove, it can go pretty fast and still recover, which is good because we can make it drive, and there it deadens its motion so it stays stationary. I give it a bit of a faster shove back this way, so we still need to keep an overhead for balancing while driving, but it's actually feeling much more stable. It's able to catch bigger movements, so we can try and make that radio controlled. And hopefully we can drive along at a relatively reasonable speed, obviously keeping that overhead so that we can still balance if we have to. And there it deadens its motion again. Back to short motions, so I think that's the best I can do really with DC motors with no wheel encoders. So how am I going to make it radio controlled? Probably using one of these, which is similar to the one I used on my R6 droid, which is a standard radio control set for cars, boats and planes and so on. This is a 6-channel version, which has 4 channels there and 2 analog pots here. And on my droid, of course, I use one for driving, and the farther you push it, the faster it gets. The challenge with this is I think there's only going to be a sweet spot where I can bias the inertial measurement unit numbers so it thinks it's leaning to actually make it drive reliably. So I don't think I need really to have all these controls. This is probably overkill. What I probably need is some sort of digital remote with buttons for forward and back and left and right, which just adds some numbers to the inertial measurement unit to make it think it's leaning. So the other challenge with this is reading the pulse width modulation that comes out the other end, which would normally drive an electronic speed controller or the servo. Actually takes 20 milliseconds in the loop for each channel, of which I need 2. So as we've seen, timing is quite critical, so that's not going to work very well. So what I'm in fact going to do is counterintuitively turn this into a digital remote control set. So I've actually got the Arduino Pro Mini now on the table. This is the radio control receiver. The data that comes out of here is pulse width modulation. So I've wired 2 of the channels as well as power to 2 digital pins on my Arduino Pro Mini, and that is currently plugged into the laptop, where I've got a little bit of code there which basically does a lot of if statements and reads the pulse in variables. And have a look at my R6 servo mixer to get some more details on that. But essentially it produces the commands. So if I push the stick to the right, it says right, left to the left, forward and backwards, and it's just using thresholds in the pulse width modulation signal, using pulse in to say if it's within certain bounds, then output that data. And what I'll do is actually output some digital pins which I'll read with the other Arduino, and that'll be much quicker than reading the pulse width modulation in the same loop as the dynamically stable loop on that Arduino, which, as I say, would take 20 milliseconds potentially to read each channel. That would really throw off the timing for the PID loop and the complementary filter. My Arduino Pro Mini from SparkFun is mounted just here on this breadboard, and we can actually take the programmer off and use that on another one, so you don't need one for each one. We only need that to program it. I've got the wires running out, and those are running into some digital pins on the main Arduino, which is actually doing the dynamic balance still, and I've got the radio control receiver just on the top here, which is receiving the stuff from the remote. So let's see how well that works. Right, so here we go. I've got a bit of blue tape on the front there, which is the front, and I'm going to put that facing away from me. I've got the longest shot on the camera I can get, so we'll just leave that there. And if I grab the remote, we should be able to see that I can coax it along basically, and I found in the end it was best to add a little value to the gyro for each axis. I tried it on the accelerometer, which did some weird stuff, and I tried it on the mix as well as the actual output to the wheels, but both of them were uncontrollable. This way it's like giving it a short, sharp shock. So if I push forward on this, we should be able to see that it rolls roughly away from me. And you can sort of compensate as well to help it balance and stop it overshooting and coming back the other way too much, just by giving it a little push. So if I push to the top right, it should head over. You should be able to see it leaning a little bit as I push the stick, and leaning in that direction. So I can come back this way a bit. It's a bit like coaxing along a drunk dog on a bungee, I would say. There we go. So I can steer it, not particularly well. I've also noted that the floor in here slopes slightly. I actually put a spirit level on it. It slopes this way, so if I go this way I have to be quite careful, because it gets carried away and ends up under the table, and then it hits the table and things go wrong. But on the whole I can just about steer this around, even if it is a bit crazy. Hooray! So what I'm doing in code here is reading some variables called forward, back, left and right, and I'm just doing digital reads on those pins, and those pins are connected to the Arduino Pro Mini. So this is on the main Uno, which is doing the dynamically stable loop. Here I've commented out where I tried to bias the accelerometer. So in fact what I'm doing is basically adding the bias, which is a variable, to X and Y, so adding it to Y or taking it away from Y if you go backwards or forwards, and the same with X on left and right. And that bias number is defined at the top, and currently that's 5 degrees. So basically it gives it a 5-degree shove on the gyro when you go and hit the stick. Now we can see that that does actually have an effect, and you can see the head of the droid leaning as you do that, but it is quite a short, sharp shock. Any less it doesn't really have any effects, and any more it just tips off the ball. So I think what we could do to improve this is to have it so it ramps up to 5 and ramps down again slowly. So whether you could do that by manually operating the stick, or whether when you hit the stick and it gets its digital in, it then ramps up and ramps down, so we get a much smoother motion as that gyro gets balanced. And that's something that I really need to go and do some experimentation with before next time. The other thing is I've tweaked the PID settings again, and they probably need playing with some more for a bit of extra stability when moving, but this is the best I can make it work within a few attempts. That's the end of this video. I probably need to do some more tuning and some more testing and bits and pieces to make that a little bit more stable, but I think I'm on the right lines. Next time, hopefully I'll have it working a little bit better, but I'm also going to paint up the whole thing to look like BB-8. So I'll be painting the ball up, and I'll also be doing some stuff on the head with some 3D printing and some other techniques to cover this dome, try and get the eye on and the other features, so it at least looks like BB-8. That's going to be part 4. After that, I'm probably going to start on a new version, which is a bit more like the one we saw on the stage at Anaheim. So don't forget to subscribe to my channel and check back for updates on this project and other projects. Also check out the links in the video description for links to my social media and other pages.